Thanks for attending this session. So we'll be talking about Linaro DDT, which is the debugger, and how we can debug on Aurora. So just before I go into that, we can kind of look at all the different supported platforms. Yeah. And the tools are cross-platform, so they supported on, let me just move some of these things. There's quite a lot going on. So it's supported on a range of different architectures, so Intel, AMD, or the ARM. Or if you want to do debugging on GPUs, we support the Intel Z, as well as NVIDIA and ROCm. And then on top of that, we also support a range of compilers and MPIs as well. So with the Intel Z HPC, the backend of DDT is actually using IDGDB. So this is the Intel distribution for GDB. So pretty much all the features that are supported in that is supported in DDT for debugging. And some of the languages that support is things like SQL, OpenACC, OpenMP Target Offload, and those kind of programming models. So languages as well, the debugger supports C, C++, Fortran, as well as Python code. So if you're debugging any ML models that's written in Python, then the debugger will be able to debug the Python parts of those codes, as well as any C parts that is available. So then just to look at some of the highlights of the tools, we have the trace points, which is kind of like a scalable print statement. What this means is that it has spark lines, and you can see how the variable values are distributed across all of the processors. And you can see this for the CPU side of the code, as well as the GPU side as well. So if you have some of your GPU threads, you can see how they are distributed, or how those variables are distributed across all of the GPU threads. So in terms of watch points, a watch point is only really supported on the CPU side of Aurora, and that is because IDGDB does not have support for watch points, which means if you try to do this on the GPUs, that's not going to work. I'm not quite sure what happens. I think it just comes up with an error that says you cannot do it there. And in terms of static analysis, there's a range of things. If you start DDT up, it gives some hints and tips of your code, just to make sure that you don't have any specific issues. And if you do, it's really good to kind of get rid of all of these warnings that DDT presents, just so that your code is written in a better way that's not going to cause issues when you run this up at higher scales, or if you run your code, it might crash, for example. And then further to this, there's also memory debugging. And again, the memory debugging is only supported on the CPU. It's not supported on the GPUs. And that's also, I think, because IDGDB does not have the memory debugging support yet. But if you want to debug on the CPU side, then what you need to do is you need to export this neo read debug key equals 1, and the neo disable deep bind equals 1 as well. And this is because the Intel 1 API runtimes, they conflict with the Forge memory debugging library at the moment. And so these needs to be disabled so that you can get memory debugging on the CPU. So just in terms of terminology, because you might be familiar with other terms, and it's just good to know what the terminology is, so that when I kind of talk about debugging and go through some of the examples, then you kind of know what we're talking about. So in terms of the execution unit, on the NVIDIA GPUs, these are called warps. On AMD GPUs, these are wavefronts. But on the Intel GPU, these are called subgroups. And depending on the GPUs, the size of them differs. So on the NVIDIA GPUs, it's typically 32 threads. AMD 64 threads, but with the Intel GPUs, this could be 8, 16, or 32 threads. The testing I've been doing on Aurora says it's 16 threads. So when you step your code, then it's typically stepping in a lockstep of 16 threads. But I think this is because it is hardware dependent. So some GPUs, when you step, it will only step 8 threads. But it might be software dependent as well. I'm not entirely sure. Then on the thread side as well, so they're called lanes with AMD GPUs and NVIDIA GPUs as well. And Intel GPUs call them lanes or work items. Okay, so when I talk about subgroups and lockstep or lanes, I'm kind of talking about the Intel GPU side of things. So then just looking at the UI, there's a range of different elements that you do to control the threads and the processes. So the first one is process controls, and this allows you to run, pause, step into, step out of functions, and those kind of things. And you can also set process groups as well. So if you have a range of threads that you just want to sort of group together to the CPU that they're connected to, you can group those together and you can step, and you'll only step those specific groups instead of you stepping everything. There's also the source code view, and this is where you are in your code. And if you have some of your host code or your device code, then if you're in the host code, you can sort of jump in between different areas of the source code view or set breakpoints there, run it, and the debugger will halt in those areas. And there's also variables. You can see a range of different variables and how they are distributed across the threads or how they're distributed across the processes, depending if you're on host or device code. Yep, so then there's also project files, which helps you to sort of jump in between different parts of your code. You can also search for specific libraries, and this helps you to kind of debug the to help you debug the CPU and the GPU side of your code concurrently. So then just looking at the debugger, sorry, the GPU side of things, you can debug the GPU and the CPU side simultaneously. And as we discussed earlier about the subgroups, so all of the active threads in a subgroup, these will execute in lockstep. So you can't, so if you're inside of a kernel, you can't step one thread at a time. It will step on Aurora 16 threads at a time. And if you press play or continue, it will run all of the GPU threads. And when you pause, it will pause that running kernel. And when you're within one of these kernels, there's a couple of additional views that DDT will bring up. So these are the kernel progress view, the GPU thread parallel stack view, the GPU thread selector, and the device pane. And this just gives you some extra bits to be able to control the execution. And what this kernel progress view does is it's a projection on a straight line of the GPU indexing system. So what you can do is you can kind of move in between all of your threads by selecting these. And this tells you which are active and which are inactive. So the white kind of says these are inactive threads, and the green says they are active. And you have light green, which means there's only kind of one kernel that's been selected, or the darker green means that there's multiple kernels. And you can see within this specific kernel progress view, there's two kernels on process 5. And then to be able to debug the GPU, what you need to do is you need to compile your application with -g or -0 flags, sorry, and -0 flags. And this just gives the debugger enough debug information to be able to um, to be able to debug your application. So then looking at the parallel stack view, this kind of gives you the location and the number of threads. And if you click one of these items in the GPU thread selector, then it will update all the variables. It will kind of move to that area of the source code view where those threads are. And yeah, if you look over the tooltip, you can tooltip over that, and this gives you the GPU thread ranges as well as the size of each of those ranges as well. Over here, when we select on this specific GPU thread, we can see that it's 8 threads, and the range of those threads as well. If you're running Python code, the debug is able to do things like spark lines for Python variables. You could do trace points or look at specific. You can look at the MDA view, which is looking at a visual display of the data that you have within your arrays. So if you have some of these complex arrays or complex data structures, you can actually view that in DDT and you get a 3D visualization of that data. You can either have a look at this and see if that visualization is what you expect. So there's also a range of different evaluations you can do. So you can do things around pandas data frames or series objects, array objects, and those types of things. And there's another feature in DDT where you can run things offline, which if you don't want to use the UI, it might be easier just to run a command line option. So you can run the DDT minus offline, and then you can set breakpoints or trace points, and this generates a HTML report or a text file, which you can use to evaluate your application. And this is kind of good for CI/CD and those type of things. If you want to just make sure that your threads are always producing the correct answer consistently, so you can change your code and just make sure that when you rerun that those lines of code are still coming up with the correct answers. So before I kind of show how you get this working on Aurora, what you could do is you can log on with -X. This is typically quite slow. So what we do is we have this client which you can install, and it just makes it much faster for you to be able to debug remotely on the system. So what you'll have is the client on your local laptop if you're Mac or Windows, and this connects to the application running on Aurora, and you can debug, and you can debug locally as if you're on the system, which is quite fast. And the way that you would do this is you need to download the client. I'll just go on to here. So we type Linaro Forge, and then you can go into downloads and documentations and download just the latest client. If you have a Mac or a Windows, you can download from that. I've already got one installed on my system. And then once you have done that, you need to set up some of these configuration settings. So in this remote launch, you press configure, just type the host name of your username and accessing Aurora, as you would do if you're SSHing to the system. And then on the remote installation directory, just put in the location where Forge is installed, which is in this opt Aurora location. And this is all in the slides that was sent out a little bit earlier. Okay, so I've got some commands here that shows how we can get started on Aurora. And oh, sorry. So as I said in the slides, we have to compile an application with -g and -0. So I've got this very simple matrix multiplication example. You can compile this with MPI CXX and -f sickle, which is because it's a sickle application, and then we give it the specific flags to get the debug information out of that. So I can go ahead and do that now. This should compile this matrix multiplication example, hopefully. There we go. And then what we can do is we can get an allocation. So I'm only going to run this on 2 nodes for the time being. And hopefully I can get an allocation quite quickly. But while we wait for that, I can just do something else in parallel. If you want to run in offline mode and you want to run this through a job script, what you can do is you can set up a specific job script, which I've done submit.sh, and you just launch this as a typical job script. So I've got 2 nodes available there. I'm using the file system Flare, and I've got the queue and the account for the hackathon. What you'll need to do first is you need to module load Forge, which loads the tools on Aurora. Yeah, I'll come back to the script just because I've got an allocation. Okay, so now we've got an allocation. What we need to do is we need to load the latest one API. And the reason for that is because there were a couple of bugs with the previous one API, and Intel has fixed some stuff, which means that at very high scales, we're able to debug everything that we need to debug now. But this latest version isn't currently on the default system. So what we need to do is we need to explicitly load the latest one API, which I've done there. And then there's some documentation which tells us how we can launch DDT on Aurora. So just like we did in our job script, what we can do is we can modulate Forge. That loads the Forge product, and then what we can do is we can set this Forge debugger wrapper script to point to this GPU tile compact.sh. And what this does is it maps the MPI ranks to the GPU tiles. And I think you'll typically do this on Aurora, even if you weren't using the Forge tools. It kind of sets up some of the GPU mappings. But if you want to do this with the tools, then you need to export this explicitly as a debugger wrapper. And then from there, there's this little helper toggle.eu debug.sh script. And what this script does is it enables the debugging on some of the on the nodes, only because this is something to do with the Intel One API. By default, the debugging is not enabled on this node, so you need to explicitly switch those on. But this little script will do that for you. So I've got this script, we just copied in and pasted the contents into this helper.debug.sh. And we need to run this command. So we need to actually run the npi exec command to switch on all of the debug on those nodes. You don't actually have to set this environment variable because DDT explicitly sets it, but if you're doing things like a remote launch, so your application is already running and you want to hook up DDT to something that's already running, then you'll need to set this. So it's probably good practice to set this environment variable. Okay, so that's all you need to do. All the pre stuff that needs to be done. But this is not a DDT issue. This is kind of just how the Intel tools currently work for you to be able to debug the GPUs on Aurora. Okay, and then from that we can do this command. And what this does is it launches DDT, and we do ---- connect, which enables us to do the remote connection. And then we can set ---- equals generic, and we set the application to run to this matrix multiplication. But I actually think I'm in the wrong location, so let me just check that. Yeah, I need to be in examples. Right. Okay, so I've set that up. So what I can do is I can launch my client. And so if you go into configure Aurora, I've already got this configured for my username and how you log into Aurora and where the latest forge is. So if I click Aurora, then it should ask me to accept this connection, which I do. And all of this would be automatically populated if DDT detected that all the tools are on the path. So this is one prerequisite actually that Forge needs. It needs to have that GDB1 API available in your environment. And I just pointed DDT to the latest one API. But the tools won't work unless it's in the environment. I need to press run. So when we run this application, we can see that all the processes have halted on this line 40. So this is where we are. And from here, because we've not hit any GPU kernels yet, they're all around this line here. So 64, there's a kernel there. And so what we can do is we can just step this, and this will just be stepping through the GPUs, the CPU. side of it. So we can see we're just going through some for loops, and we can see all the variables and the sparklines so that they all are exactly the same across all of the processes. And we can set a breakpoint here and just run to that specific breakpoint, and you can see all of these processes have stopped on this breakpoint. But if we want to do some GPU debugging, what I've done is set a breakpoint within this kernel. And if I run that now, you can see some input output of it doing the matrix sizes. You can see some of these processes are stopped while some of them are still busy running. We just have to wait for those to complete its run. There we go. So when this is halted on this breakpoint, what we can see is now we have this kernel progress view, and we can look at the GPU devices as well. So there's Intel R data center GPU max, and these are the ranks that they're on, as well as how many cores there are available. And we can look at this thread selector as well to select some of these threads. And as we click through these, we can kind of iterate through all of the available threads on the GPU. Or we can just go to the progress view and click through this one. You can see this thread selector updates. So you know which thread that you are connecting to. So because some of these processes are so they are within a kernel and others are not. So others are on a different side of the code to the CPU. We can kind of break these up to kind of say, well, we just want to step through and run those that are running inside the kernel, but we want to leave those alone that are still on the CPU side of things. And we can do this by creating groups. We create a group of GPUs. I don't know, they're on from 0 to 11. Let's just double check that, yes. And then we can create another group from 12 to 23, which are the CPUs. Has to be this one. And then we have two groups. I'll change the colors a little bit just because I like them to stand out a little bit better. And so now what we can do is we can just control the GPUs, or we can just control the CPUs if we wanted to. So from this, we can just step. There's no kernel progress view because we're not within inside the kernel, and we can just step these CPUs. And we can run this, and we'll leave everything that's within the kernel alone. And then likewise, if we want to just go through this kernel and we want to just run through all of this, we can do that, and we can just run those. It's going to take a little bit longer because there's a lot more threads to get through to be able to do these calculations, and so it's a little bit slower. But it should constantly hit these breakpoints. Okay. So just a note about the breakpoints with the Intel Z GPUs is as soon as a breakpoint is hit, So all of the GPU threads within the subgroup needs to hit that breakpoint. And if there's a divergent in your code, so if you have an if statement and only some of those threads hit those breakpoints and the others kind of don't go through that if statement, they take another path, then only those threads that has hit the breakpoints will be visible, and everything else will be hidden. So anything that hasn't hit that breakpoint will be hidden from the view. Which means that because we've hit this breakpoint, only the active threads we can see. And so from the stack view as well, as we said, we can kind of look at where all of your threads are. There's 688,128 threads on this line. And there's quite a lot on this line as well. So this is where on the threads line, we can kind of hover over this. You should be able to hover over it. I'm not sure what's going on. Just give me a second. I think I've got to click on threads. So if you click on threads, yeah, that's better. So you can look at all the groups, which kind of looks at the processes, but then you can click onto threads to kind of control the actual GPU threads, and you can see where all of these GPU threads are. And this is giving the sizes and the location of all the threads. So you can see 16 threads on this line, and all the other threads are on line 87. But I think this is actually the stack. And so we can also select which kernel we're on, and then we can step within that specific kernel. But because it's only stepping 16 of these threads in dogstep, only of the 16 of the threads will continuously be on the specific line. And as it updates, so this is hit and another part of the code, so we can sort of step back into that. And then we're back here. So this has kind of gone down into another path somewhere, and we can kind of step out of that. And every time that we run or we step, then all of these local views or these local variables, they get updated. And these are for each one of these threads. So we can kind of click through all of these threads as well, but all of the values are exactly this. Oh, no, they're not. So you can see the column is 389. And as we kind of go up this, 390. So each column is related to each one of these specific threads. And likewise, if we go down to the rows, we can see how these variables are updating depending on which thread we selected. So each one of these threads will have a different variable value. We can also set trace points here, and what trace points does is instead of you having to put print statements and printing out all the values of each one of those threads, what you can do is you can put trace points there instead, and as your application is busy running, it just prints out the values. So if I add a trace point in here, okay, that's a bit strange. There we go. Okay, so for some reason you can't put a trace point on a specific thread. You have to put the processor which puts it across all of the threads. But so if we just click on this group, and if we run that, we should be able just to see the trace point output. So what the variable values are every time that this line of code gets hit. So I need to remove this. Okay. Yeah, so the application actually finished. So I wasn't able to iterate over this enough times to print this. But what should happen is if you run that, you can kind of print out all the values across each one of these threads. But if you run to the end of the application, you can just restart the session. And what this will do is we'll go back to the very beginning of your application. And so you can just rerun everything. And for this, I'll just run that. This should produce an, I'm not sure why. I'm not sure what's going on there, but what should happen is the those values should get printed on the command line console. I'll need to play around with that a little bit more. But what I want to do is kind of just move on to something else. So that's how you kind of use the debugger, and how you can kind of step through things and evaluate all of these threads and the variable values of those threads. Okay. So just going back to this job script that we spoke about earlier, we just putting these commands into a script. So we're doing the module load forge, and we're exporting this forge debug wrapper, and we're setting the tools to point to the latest one API, and then we're running this script to enable debugging on all of the nodes that we have reserved. And then what we can do is we just run DDT minus minus offline, or we can do DDT minus minus connect. If we do DDT minus connect, then as soon as we get a allocation, we can connect to that with a remote host, and then we can just do the debugging as we did before. But for now, I just want to do minus minus offline, which gets an offline log for us. And this is just to kind of show that you can put DDT within the job script, and once allocation is reserved, then you'll be able to debug your application. Yes, that'll go off in the background, and once it gets an allocation, we can come back to that. Let me just bring the slides back up very quickly. We talked about memory debugging, and we said that we need to export these near read debug keys equals 1 or near disable dbind equals 1 to make sure that the one API and libraries do not compete with the Forge library. So we set these. Yeah. And then okay, so we set those to there, and then we can do this DDT connect again. So the only difference here is what we're going to do is we're going to enable this memory debugging. Okay, that's interesting. I think what's happened is I need to go through all these commands again. It's very strange. This shouldn't really happen. Let me just set these again just to make sure it's not that. Right. Hopefully this works this time around. Because there was this issue with Intel where if you disconnect it from DDT, then what you had to do is you had to get a completely new allocation and then do all these commands again. So I'm hoping that's actually fixed, and we'll see. Okay, yeah, that's fine. So I think that issue is fixed. The only difference is we might still need to set the debug flags on the nodes each time you disconnect from DDT and reconnect. The difference here is what we've done is we've enabled memory debugging. So if we run that, yeah, okay, so this gives an error, which is what we expect. And the reason for that is because there's some invalid pointers. So what DDT has done is it's forced a specific memory issue. And what we can do is we can kind of look at these the memory usage, which takes a bit of time to populate because it needs to collect quite a lot of memory information. As I said, this is not memory on the GPUs, this is just on the CPUs. And um, okay, so what this is showing is that all of these ranks, so from rank 0 all the way to 10, we can see that it's a flat distribution of memory. We have a main code here, and we can see all the different allocations that we've done on each one of these ranks. I'm not really sure what this load context is, but I think this is probably some third-party library that's using some of the memory. We can also kind of look at the allocation, so what's being allocated at this point in time, which is a range of these. And yeah, so this is our main function, which has allocated memory, but it didn't deallocate anything. So what we can probably see, it might be just some memory that needs to be deallocated in a matrix multiplication example. And we can dig further into this as well by looking at the overall memory stats. And we can kind of see what's in terms of total bytes, how much got allocated. You can see, well, we're deallocating a lot less than we are allocating in terms of bytes. We can also do this from the table view, so we can see how much is being deallocated here. So we had 201 megabytes that was allocated, and the current allocation is 35 megabytes. So that's quite a lot that hasn't been deallocated yet. Because if you think about scaling this up or running across more processors, then all this memory does add up. So you want to kind of fix that area to kind of make sure that you're deallocating some of the memory. But there's also this invalid pointer issue that needs to be fixed. So we can kind of have a look at that. Okay, well, there's not enough time in this session to kind of drill down into this specific memory issue, but this is just kind of showing how you can do memory debugging on Aurora with DDT. Okay, so this is our job that we ran earlier. We can see it ran to completion. So it's got all of the matrix multiplication results back. I'm not sure. So the important thing is we've got this matrix mul.html file, and we can copy this off of Aurora, but I've done this earlier. And it produces this HTML file. And what we can see is the output of this and just some information on the application that ran. And what we want to do is we want to kind of build up this report. And the way that we can do this, we can kind of change the job script to set breakpoints, and every time the breakpoint is hit, then it prints out all the variables and all of the evaluations or anything that you want to track. And the way that you do this, if you modify this, yeah, you can do offline, then minus break. $197, okay. So you need the name of the application, and then the actual line number that you want to break on. And every time that line gets hit, it will print out the all of your variable values. So there's not enough time probably to wait for this to come back. There's only like 2 minutes left. So is there any questions on this before we finish? As I said, I sent out the slides, which gives some all of the specific commands you can just copy and paste into Aurora, which will get everything set up, and then you can connect with DDT, and you should just be able to debug your applications. Okay, so that's pretty much everything that I had